So this one is actually almost identical to, in this case, you will be given KSP and you will find solubility. In the other example, we were given solubility and we found KSP. So it's very similar to the first one we did yesterday. The only thing that is new is that you need to make a let statement, right? Because the solubility is your unknown. So you need to say, let X be the molar solubility of whatever the salt is, okay? And then, just like before, you write the solubility equilibrium equation. So have we met a KSP problem where we don't write the solubility equilibrium equation? Not yet. Nope. And then for this one, underneath the C, you can write the X's in their correct proportion, because remember, the molar solubility is the maximum concentration of A to B. Yes? And so our concentration of A to B is X molar. Yes? And that means that if you have two A's, it's going to be 2X. And if you have one B, it's going to be 1X. All right? You write your KSP expression. Is there any case so far where we have not written a KSP expression? No. So write a KSP expression. And then at this point, you will be given a KSP. If you are not given a KSP in the question, where would you look? Page 5. So this is either going to be given in the question or on page 5 of your data booklet. All right, and the only thing to be aware of is when you square 2x, you have to square both the 2 and the x. Yes? And then you would solve for x. And whatever you get for x, well, we said the x is the solubility, and you have to remember that you include the unit in the solubility. Okay? Now, you might be asked to find the solubility in grams per liter, in which case you just have one extra step. You would take your moles per liter and you would multiply by the grams per mole, and that would give you grams per liter. Yes? Okay. Okay, shall we try silver iodide? Do you guys want to try it yourself? Because the instructions are all there. Give it a go. Yes. Did you guys get 9.2 times 10 to the minus 9?
Yeah.
Excellent. Okay, I apparently can't make the dot look like a dot. It just keeps wanting to add a line to it. Anyway, that's a decimal there. Whew, that worked. Okay. Do we have another one on the next page? Shall we try it? Now, I didn't put in the scaffolding for you this time, so see if you can scaffold it yourself. Okay, follow the same steps. You can always flip back to the page before, write the let statement, etc., etc. No, you're okay, fine. X will be molar solubility because when you're solving, it will solve in terms of molar and then you will convert. Yes. So when you're putting in the X's, they're all concentration and moles for there. Yep. You got it. Okay. No worries. No, we're going to solve that instruction for the molar solubility. Later we'll put it in red. The X will actually make it. Yeah, the molar solubility of whatever. Yeah. Once you have the molar solubility, if you want ground fluidity, Oh, nice sister. Yeah. Oh, here. Okay, let's move on. Okay. Oh, you know why? Because up here in my example, this was 2x and x. Down here, that's x and x. So it'll be x and x. And we won't square anything. That's okay. We're following the model just really, really well. Oh, by the way, I didn't point out that you can tell that this is a mix and match, or not a mix and match, a dump and stir problem, because we have only one substance. And that's why we have a 3-to-1 ratio between the two ions. Okay? Sorry about that. I totally forgot. And if any of you do like me, and if you cubed 3 and got 9, just remember 3 cubed is 27. Just saying. It's my favorite mistake, is to cube 3 and get 9. Yeah? Ah, how many people are like me? Anybody? Yes? Excellent. Do you guys know how to do the fourth root on your calculator? Yeah. If you don't, call me over. Or if you've forgotten, if it's been a while. Did you get 1.1 times 10 to the negative 8 grams per liter?
Yeah.
Whew. Okay. Now, all of this work, other than maybe, you could skip an algebra step or two, right? You don't have to show this. You could go straight to here, for example. But other than skipping an algebra step or two, you need to show all of this work for a written response question, because this is going to be worth like 4 marks, right? So you need to show everything to get your 4 marks. But if you're doing a multiple choice question, do you want to do all that? No. And most of the time in a multiple choice question, you will either have a 1-to-1 ion ratio, like a salt AB, yes, or you'll have a 2-to-1 or 1-to-2. Those are the 2 most common, okay? Yes? No? Okay. Most common. And if you happen to know, if you let x be the solubility, if you have a 1-to-1 ratio, it is going to be x squared. Yes? And if it's 2-to-1, it's going to be, this comes from having 2x squared times x. It's going to be 4x cubed. Okay? And if you're having trouble seeing where that came from, you can always go back and say, okay, I want an A to B example. Oh, I've got an A to B example right here. Yes? So on my first page, I can say, when I have A to B, I end up with a 2x and an x. I square the 2x, and I have an x. So I now have KSP is equal to 2x squared times x. That's going to equal 4x squared times x, which is 4x cubed, which is equal to the KSP. Okay? It's good to just throw those into your memory, though, so you don't have to think about it very hard. Okay? For a multiple choice question, it just makes your life easy. And there's some exercises here, fairly straightforward. We are going to move on to 3.3e. Maximum and minimum problems. Okay. See if I typed that right. Oh, I did. Yes. Okay. And I turned
we'll show
off
you how to
the
do
sound. So give me a second. So this is now on page 69. 69. And let's see, do I have sound here? I do. Okay.
problems involving concentration. Here, we'll show you how to do problems involving concentrations of ions just before precipitation occurs. In one type of problem, we are given the concentration of one ion and asked for the maximum concentration of another ion that can exist without forming a precipitate. It is important here.
Now, if you have the maximum concentration and not form a precipitate, what do the ion concentrations have to multiply to equal? Remember last day, if you multiply the ion concentration, you get a number that is too big, you'll get a precipitate. And when we say too big, what are we comparing our ion concentrations to? We're comparing them to our KSP. So if the ion concentrations multiplied together are bigger than the KSP, we will get a precipitate. If the ion concentrations multiplied together are smaller than the KSP, we will not get a precipitate. What if we are exactly at KSP? We are just barely saturated, which means that's the maximum ion concentrations that we can have if you add one more drop, precipitate of either ion. Like, so if you add one more particle of either ion, you will get a precipitate. So you want your ion concentrations to multiply together to give you KSP. So you'll be using the KSP value here. You'll be given one ion concentration, and you'll need to find the other ion concentration. This is actually the easiest problem of all because we have KSP. Let's just say we've got a really easy one, just A times B. If I gave you KSP and the concentration of A, could you solve for B? Yeah. If I gave you KSP and the concentration of B, could you solve for A? Yeah. And even if we made it crazy, oh, let's make it crazy. Let's make that 2 plus and that minus and that squared. Could you solve for the concentration of B?
Yes.
Yeah, because you would just take a square root when you get to the end, right? Okay. And yet, people get these questions wrong all the time because they start overthinking it. And they start trying to make the concentrations proportional to the coefficients. Don't do that. Let's just see where we go, and I'll mention that again.
Here to realize that the two ions in question are coming from different sources. They are not coming from the same compound. So the concentrations of the two ions in question will not be in the simple ratio of coefficients in the solubility equilibrium equation.
You would think that students all over the province have the same issue with this question. And in fact, they do, okay? I've been harping on it for 28 years. Mr. Colger, obviously, harping on about it. Okay, this is a mix and match problem, all right?
For the possible precipitate. They would be only if they were both coming from the same compound, but here they're coming from two different compounds, one that's in the beaker and the other one that's added to the beaker. In another type of problem, we are given the concentration of one ion and asked for the minimum concentration of another ion needed to just start forming a precipitate.
Okay, let's remind ourselves. If we have the ions concentrations multiplied together and the concentration is too small, do we get a precipitate? No. If it's too big, we get a precipitate. If it's exactly equal to KSP, we don't get a precipitate, but like one drop over and you will. So essentially, we're on this like knife edge, right? It's like one drop too little, no precipitate. One drop too much, precipitate. Yes? So we actually can give the same answer here. Okay? Usually what we'll do is we'll say, what is the minimum ion concentration needed? We'll say just greater than whatever we've solved for. Okay, just greater than whatever we've solved for will cause the precipitation. Does that make sense? Okay, but even if you were just to say this concentration, I would still give you credit. Okay? Okay. So they're really the same question. And in both cases, I will give you the KSP and I will give you one of the ion concentrations, and then I'll say, what's the minimum or maximum of the other one? You just solve for the other one. Okay? Like grade 9 algebra, right? Like easy peasy.
Actually, these two problems are really the same. When considering maximum concentration without forming a precipitate and minimum concentration to just start forming a precipitate, we're right on the verge of forming a precipitate with the two ions in question. So we can simply use the KSP expression and the concentration of one ion to find the concentration of the other ion.
I'm just going to pause there if you want to fill in the blanks there. Okay, are we good?
Let's do an example problem. We are given that we have 2 liters of 0.01 molar copper nitrate solution in a beaker. We're asked the mass of solid KiO3 that would need to be added to this solution to just start precipitation.
So, is this dump and stir or is this mix and match? So what I would like you to do is I would like you to, just like we did last day, I want you to think about which compound will we write the solubility equilibrium expression for. Okay? You think about that, and then after you've thought for a minute, I'm going to give you some choices. Okay? Can you guys give me one of the choices? Okay, well, we're going to start with the ones that are given in the question. We're going to start with copper 2 nitrate. Cu NO3 2. We also have KiO3. Now, if we combine our K and NO3, we will get KNO3. And if we combine our Cu with our IO3, we get CuIO3 2. So tell your partner which choice you like. And remember, we're going to vote. And this is letter A. This is letter B. C. And D. Now, the letter D, you put all your fingers together except for your pointer finger. Your pointer finger points up. Just the pointer finger. Yeah. If you do like this, that's an F. This is a D. Okay? So, which one do you guys like? You like option D because it is the only one that is low solubility, right? All the rest of them, the copper nitrate, potassium iodate, potassium nitrate, those are all soluble, soluble, soluble. You will not write a solubility equilibrium equation. So when you're looking at this, you say, in order to get copper iodate, I had to mix copper nitrate and match it with potassium iodate. Yes? So this is mix and match. We have two compounds mentioned in the question. Yes? So the copper is coming from one place, the iodate is coming from the other place. And that's how you can tell that you will not have a 1-to-2 ratio between copper and iodate. I wonder if you guys could just grab yourself a piece of paper and see if you could solve this problem. Yeah? I'll come around with paper because you guys are really bad at grabbing paper. See if you can solve it before Mr. Colger lets us know. You don't have to have the paper. If you don't need paper, just wave me away. And if you get stuck, remember what we do in every single question, right? The solubility equilibrium equation and the KSP. Anyone need paper? Do I need to leave that too? I would start by writing the solubility equilibrium equation and then I would write the KSP. Usually because you can figure out what your KSP is based on your solubility equilibrium equation. No, they are all the atomic ions, so they should put that out. Yeah. No, it's not. If you ever see something like in brackets, you're going to get a lot of time to state that. You do not get that not putting proper iodine. One chamber copper. Yeah. And we want to know the concentration of iodine. So iodine is unknown or obviously known. And look up. So your X is going to be iodine. We'll assume that it does not change at all. Dump this mass. So what's the problem? Yes. Yeah. Yes. It's not? All right. I know. Okay, which one are you ready to see for? The low solubility one. What are you gonna do with this? That just, it's a one-way arrow, it dissolves completely. Yeah, you don't want that at all. Yes. Now, where did those come from? Okay, what is the concentration of the copper? So is that an unknown? No. So folks, I'm gonna let Mr. Colger show us how to do the problem. So if you're stuck, Mr. Colger is gonna show us, we'll walk through this. Because a lot of you are trying to solve this using X and 2X. And it doesn't work like that because this is a mix and match. They will not be proportional in a 1-to-2 ratio. What do we actually know here?
Copper.
We know the concentration of copper. It's not an unknown. Copper concentration should not be a variable. It is a known value. And the KSP you can look up on your table. So let's let Mr. Colger walk us through this just to make sure that we're all kind of getting it, and then we'll do another example.
We assume that the addition of a small amount of solid KiO3 will not affect the total volume of the solution in any significant way.
And we always make that assumption that when we're adding a solid, it does not affect the volume, okay? At least not significantly.
We'll dissociate KiO3 into its ions, which are K plus and IO3 minus. And we'll also dissociate CuNO3 too, to give us the ions Cu2 plus and NO3 minus. NO3 minus, or nitrate ions, and K plus ions are both spectators, so we can discard them from our discussion and tidy up. We'll show Cu2 plus ions in the beaker.
Okay, so I'm just going to pause that for a second. Did you need me to go back at all, or are we good? No, we're good? Okay. So we know copper ion. We don't know how much iodate. Iodate is our unknown.
Like this. When we add a small amount of solid KiO3 from the spoon, we're actually adding IO3 minus, or iodate ions, to the beaker. If the concentration of iodate ions is high enough, some of the ions will move together and form the precipitate CuIO3 or copper-2 iodate. We want to know exactly how much KiO3 needs to be added to just start the formation of the precipitate copper-2 iodate. Since we know that the precipitate would be copper-2 iodate, or CuIO3, we can now add that to our question. There's lots of steps needed to complete this problem, so it's best to create a plan first, listening in steps. Step 1 is to write the solubility equilibrium equation for the precipitate.
And that's our step 1 all the time, isn't it? Write the solubility equilibrium equation? Yep.
CuIO3. In step 2, we use the equilibrium equation to write the KSP expression.
And again, that is always our step 2.
We can easily determine the concentration of Cu2 plus from the given concentration of copper-2 nitrate. So in step 3, we put this into the KSP expression and solve for the concentration of IO3 minus needed to just start precipitation. In step 4, we use the fact that there are 2 liters of solution to convert the concentration of IO3 minus to moles of IO3 minus. We're asked for the mass of the compound KiO3, so in step 5, we convert moles of IO3 minus to moles of KiO3. Finally, in step 6, we'll convert moles of KiO3 into grams of KiO3.
Are we okay with going from IO3 minus to KiO3? moles of IO3 minus. We found that using the KSP expression. We will have found that. Are we okay saying that the moles of IO3 minus are the same as the moles of KIO3? Because it's a 1-to-1 ratio. If you had a compound, like let's say you had calcium iodate, and you had 2 iodates, you would have to do a unit conversion. Okay, you'd have to use the mole ratio. Okay, but here it's just 1-to-1. All right, let's see how it goes.
And that's the mass that we're asked for.
And now we're on
We'll
page
start by
72.
writing the equilibrium equation for copper 2 iodate. Notice there is 1 Cu2 plus and 2 iodate ions. The KSP expression is Cu2 plus times IO3 minus squared.
So you can check that you have that correct. CuIO32, and then you should have a Cu2 plus and a 2IO3 minus. You don't have to fill it in on page 72 if you've already done it like yourself, okay? But you can if you want to. And then our KSP, Cu times IO3 squared. And then we solve for IO3 squared. It's usually easier to just leave it like that and toss in the numbers and then take the square root. Yeah? So do we know a value for the KSP? Where did you find that?
Page 5.
Page 5. Okay, so you will go and you will look up your KSP from page 5.
In step 3, we want to find the concentration of IO3 minus. We start by rearranging the KSP expression to solve for the concentration of IO3 minus squared. Taking the square root of both sides gives us the concentration of IO3 minus is equal to the square root of KSP over the concentration of Cu2 plus.
Now you can either do this square root process over top of the symbols, or you can put in the numbers first, solve, and then take the square root afterwards. It doesn't matter.
We'll rewrite this expression up here. And we'll replace the symbol KSP with the actual KSP from the table. Looking up the KSP of copper 2 iodate, we find that it's 6.9 times 10 to the negative 8. So we substitute 6.9 times 10 to the negative 8 for KSP in our expression. Now we have to find the concentration of Cu2 plus. We see at the bottom that the solution was 0.01 molar copper 2 nitrate.
Yes, 0.01 molar copper 2 nitrate, 1-to-1. So if this is 0.01 molar, then copper is also 0.01 molar.
Looking at the dissociation equation for copper 2 nitrate, we see that the coefficients on Cu2 plus and CuNO32 are both 1. So since the concentration of CuNO32 as a whole is 0.01 molar, it means the concentration of Cu2 plus from the salt is also 0.01 molar. So we'll substitute 0.01 molar for the concentration of Cu2 plus in here, like this. Dividing 6.9 times 10 to the negative 8 by 0.01 and taking the square root gives us the concentration of IO3 minus is 2.63 times 10 to the negative 3 molar.
All right, so if you have not made it that far, you can copy this down. And I would like you, if you have not gotten past this point, to now try and figure out the moles of KiO3 and then the grams of the moles of IO3, the moles of KiO3, and the grams of KiO3. Okay, so you're going to try, once you have the iodate concentration, to find the moles, and then the moles, and then the grams. Yes. I heard my name. Yes. No, because the concentration is increased.
Because the moles be in one of it. Always.
There's a way.
Mole per liter. Yes. So you'll end up using that when you find a concentrated iodate. Find a moles there. Okay, now. That's good. So now you have moles of iodate. Now we can find the moles of high, low, or freeze. What's the relationship between moles of iodate and moles of iodate? I don't remember. Green mass would be the ground static. Oh. You're right about Cindy. Okay, now, remember, we already did a phone you read. I want to find Right, so you have moles through, right? And if you want to find moles, we can mold by that.
That's right.
Well, that was counting. What we want, we want it all by itself. What's causing up the L. That's okay. That's not, yeah, absolutely. Okay. And then, yes. This one. Okay. Makes sense? Yeah. 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 Good. Yeah, if it were a test, I'd take home actually, I figured, yeah, I'm like that. How you doing? Okay. Moles per liter. And did you ever multiply by 2 liters? Yes, you did. Very good. Okay, very good. Yep, you're good. Little confused? Okay. Okay, so you have now, so here's the thing.
you want to find moles, right? We're finding moles of IO3. Do we want to cancel moles? If we want to find moles? No. So what's cluttering up the moles? The unit we don't want. We want to find moles. Right now we have moles per liter. Well, we eventually want grams, but let's do one step at a time. Okay, so we have units here. Right, we have liters here. I don't want moles per liter. I just want moles. We need the liters to cancel. So we're going to multiply by liters. And you don't need anything on the bottom. If you want to put something on the bottom, you need the number 1. Okay? And how many liters do we have? 2 liters. Yeah. And that'll give you your moles. I'm going to let Mr. Colger go ahead and walk you through it if you're stuck. But I think most of you are doing really well.
In step 4, we want to calculate the moles of IO3- in the solution in the beaker. We see at the bottom that we have 2 liters of solution. Because moles is equal to molarity times liters, moles of IO3- is equal to 2.63 times 10 to the negative 3 moles per liter times 2 liters.
Now, a lot of people got to that point and they're like, I got moles per liter, and you're so used to multiplying by this over that, right? And so people were trying to put moles in there and things were all working out all weird. If you have moles per liter and you just want moles, you just need to cancel the liters, and you don't want anything on the bottom because now you would have moles. Yeah?
Which equals 5.26 times 10 to the negative 3 moles of IO3-. In step 5, we want to find the moles of KIO3. KIO3 contains 1 IO3-. So moles of KIO3 equals 5.26 times 10 to the negative 3 moles of IO3- times 1 mole KIO3 over 1 mole of IO3-.
If you don't write that step, it's okay. You can just say moles of KIO3 are equal to moles of IO3- because it is 1 to 1. Okay, you can just do that.
And that equals 5.26 times 10 to the negative 3 moles of KIO3. In step 6, we want to find the mass of KIO3. So we take the 5.26 times 10 to the negative 3 moles of KIO3 and multiply it by the molar mass of KIO3, which is 214.0 grams of KIO3 per 1 mole of KIO3. Notice the moles of KIO3 will cancel out. And the final answer comes out to 1.13 grams of KIO3. Some of the values we used in this problem were only 2 significant figures, so we'll need to round our answer to 2 significant figures, which is 1.1 grams of KIO3. So we can say that 1.1 grams of KIO3 would need to be added to 2 liters of 0.01 molar copper-2 nitrate solution in order to just start precipitation. Now, if you put in exactly this amount, it is right on the verge of starting to form a precipitate. You wouldn't notice any precipitate yet. If you added a tiny bit more, then you would start observing a precipitate. If you want a copy of this problem and the whole...
Okay, now, we are on page 73. And basically it just, if you weren't here for the whole presentation, right, this just summarizes what we've been talking about. Maximum and minimum problems, you're either looking for the maximum without a precipitate or the minimum to cause a precipitate. And they are the same type of problem. When Q is equal to KSP, the solution is just barely saturated and we get no precipitate forming. You plug in one of the ion concentrations and you find the other ion concentration, but don't try and make them equal X, just the one ion concentration. If you want to use X for one of them, that's fine. Okay? And then we have all the steps, identify the precipitate, right? Which compound will we write the C for? Yeah, that's what you're always asking yourself first. When you have a mix and match problem, how do you know you have a mix and match problem? You have two compounds, and they will both be soluble. You need to find the compound that they make that is low solubility. Okay? Don't try and use the soluble compounds. You will get nowhere. The question will just be like, you'll just be throwing numbers around, and like I'll have to like look at it and it'll make me sad. So always look for the low solubility compound. Then you write the C, then you write the KSP, you plug in the KSP value, you plug in the 1 ion concentration, and you solve for anything else the question wants from you. Do you guys want to try one more? Do it. Your homework for tonight is going to be to study for your quiz tomorrow, which is on 3.2. None of this math is on the quiz. It's all about shifting and increasing solubility and decreasing solubility. Okay?
So it's the one.
Uh-huh. Yeah. And you can actually do this in your book because it's on the next page. There you go. Yes, that's correct. Yeah. You are. There you go. Does the shifting matter in terms of concentration of the compound? In this case, no, because we're adding a solid. We're adding a solid phase isolation, so we're not adding a Okay. Okay, so you're going to identify what precipitate. So this is very much like the previous quiz that we did, where you're going to mix this and you mix that in and say, who are my products? So you would combine your outside ions, the Na and the NO3, inside ions, the Pb and the SO4, and then you would look and see which ones are soluble and which ones are not soluble. Yeah.
Oh, dump and stir versus mixing them up. Okay, so when you dump and stir, basically you're taking the compound, the low solubility compound, dump it in the water and you stir it. So let's say we have magnesium hydroxide. I'm a huge jar. This is magnesium hydroxide. Have a little stir it until no more dissolves. Now, magnesium hydroxide, when it dissolves, it's MgOH2, so you'll get 1 Mg and 2 OH. So they will always, in fact, just added MgOH2 levels, 1 magnesium. Does that make sense? Okay. Now, mix and match is what we just did here, right? We've got two different compounds. We've got copper nitrate, soluble, and we have calcium iodide, which is soluble. We treat it like we have lost position side ions, side ions, and then we figure it's a solid. Okay. And because the copper is coming from one compound, and the iodide is coming from a different compound, they're not going to be present in one. Because it's not like you're taking copper. So, right? You have control over the copper, separately. Right, so they will not be before. So anytime you have to compound, you're looking for who's the solid product. That's what you're going to see for, right? And the ion concentration will not be like one or one, okay? Yeah. You're welcome. Right? Okay, so, so do you see this one here? Okay, so a 4 liters is actually one. No. I want you to raise it. So you're plugging in the wire. That makes you unhappy. Oh, goodness. And you could raise it to the power of over 1 divided by 4. Yeah. Okay, so a square root is x to 1. A quarter is x to 1. Take a cube root is x squared 1 over. Oh, we went on square root, but we can. No, wait, I don't. I don't know. I would say. Oh, I got to see it. Read that.
So try to always prove that they're the same.
Yeah, yeah. Good. Here's my pen.
Did you guys get a sulfate concentration of 3.6 times 10 to the negative 4 molar? Yeah. Okay. I think we have another, do we have another 5 minutes, or is this the one? No, this is short. So we're almost there. It's in the worked answer key, so you're welcome to check that out. But your homework is to study section 3.2. No math.
No math.
No math.
Oh, we did for math. Like 4 questions that involve math.
Oh, that's not in 4.3.2. Where?
Oh, no, it's like, okay.
No math. No math in 3.2. No math. Thank you. No, those are just you. Yeah. How are you?
Good, good.
Good.
This year that water needed.
Excellent. We need some water.
You guys are great. Last thing I'll